Welcome back to machine learning. Today's lecture is going to cover decision trees. In this lecture, we'll cover what is a decision tree and how do I generate one. Decision trees are a machine learning model. We'll learn about a lot of different models in this class, and this is going to be the first one and one of the more simplistic ones. Let's start with an example. If we have some data, here we have 4 samples, and we have 2 features, sunny and greater than 90 degrees. And then we have our label outside. The problem here is we know whether or not it's sunny outside, and we know whether or not it's greater than 90 degrees. And we're trying to predict if we should go outside. We have 4 samples, and I've labeled them 1, 2, 3, and 4 so we can refer to them easily. But the sample number is not a feature. We can think about this as being 4 different days. And on the 5th day, I'm trying to predict whether or not I want to go outside. We have a binary problem here. That means that the label that we're trying to predict, outside, has a binary value, 0 or 1, or in this case, no or yes. We also have binary features. The binary features are also going to have a no or yes value. We just start by building a tree. Okay, so we start at the root node by asking about one of the features. Let's just start with sunny. So if we say sunny and then we have 2 branches, no or yes, the data becomes split. If it's not sunny outside, we have samples 3 and 4, and if it is sunny outside, we have samples 1 and 2. Now, typically when you're building the decision tree, you keep track of all of this information, specifically the samples that are in your subset, depending on which way you branched. But we normally don't write these things down. So I'm going to write them down here. You can see them here, but you don't want to do that all the time, and that's not what the final tree is going to look like, as you'll see in a minute, okay? But this is just while we're working through the problem, we'll keep track of what samples we're looking at. What if I built this tree and I was like, okay, I'm done? If we stopped right here, how would we do on the training data? So the training data is this data that's available to us that we're using to build this tree. Well, let's look at it. Let's see. Samples 3 and 4 have a label of no, so I shouldn't go outside. Okay, and samples 1 and 2 have a label of no and yes, respectively. So how well could we predict whether or not we should go outside? Well, we could say no if it's not sunny, right? So on the left-hand side, we could say no, and we would get 2 out of 2 correct. And then we could say yes on the right-hand side, so if it is sunny, and we get 1 out of 2 correct. So overall, we would have an accuracy of 75% on the training set. But we could also say no on the right side and get 75% on the training set. That's not so great, right? Because why do I even have to build a tree then? Well, it turns out on this particular data set, if we just say no all the time, right? If our model just says don't go outside, we'll get 75% on the training set. So building this model here with sunny doesn't really do us any good. Well, then let's ask another question. First, let's look at the left side of the tree. We can see that we have 2 samples on the left side of the tree, and both of them have a label of no for outside. We don't need to ask another question if both of those have the label of no, because we can just say no and be done with it, and we'll get 100% on that side of the tree. Let's move on to the other side. On the other side, we have a label of yes and a label of no, so we're getting 50% accuracy on that side of the tree. If we ask a question about the other feature, which is greater than 90 degrees, maybe we can do better than 75% accuracy on the training data. We ask this question and we have no and yes as the answer. And on the no side, we have sample 2. And on the yes side, we have sample 1. So it turns out on the left side, sample 2 has a label of yes. And on the right side, sample 1 has a label of no. So on the left side, we can say yes. And on the right side, we can say no. And now we're getting 100% on the training set. This is what our final tree would look like. It's simply questions about the features, and then at the leaves, it's a decision, a no or a yes, because we're dealing with a binary problem. What's the point of this? Well, the point is we save this model, which is just a tree, and then we take new samples of data, right? So on day 5, we take the information for day 5, including whether or not it was sunny and whether or not it was greater than 90 degrees. And then we make a prediction about whether or not we should go outside or whether or not we did go outside. If we take this sample 5 and we see it's not sunny, that means we go to the left immediately and we say no. Okay? So if day 5 hadn't happened yet, our model would say, don't go outside if these are the conditions. Okay? And if day 5 had happened already, it would have said, okay, you shouldn't have gone outside. I don't know what you did, but you should not have gone outside. It's just making a prediction based on what it has learned, and it only learned from days 1 through 4, right? We can see that sample 5 exactly matches sample 3. This begs the question, could we have created the decision tree differently? And the answer is yes, absolutely. I arbitrarily chose to start with sunny, but we could start with 90 degrees, okay? If we start with 90 degrees, no is on the left, yes is on the right, and we get 50% accuracy on the left and 100% accuracy on the right. So how well would we predict going outside on the training data? Turns out it'd be 75% again. If we start with 90 degrees, we have sample 2 and 4 and samples 1 and 3 separated. On the right-hand side, for samples 1 and 3, the labels are both no, so we can just say no and move on. On the left-hand side, we're getting 50% accuracy, so we should ask another question. The only other feature we can ask a question about would be sunny. With sunny, we now only have one sample on each side. So on the no side, we have sample 4, and on the right side, which is yes, we have sample 2. With this, we can predict no on the left side and yes on the right side, and we would get 100% accuracy on the training set. This is what our final tree would look like if we started with 90 degrees instead of with sunny. Again, the sample information is not actually saved in the tree because we don't have that data at test time. We just have the tree, which has all the nodes and the branches and the leaves. And the leaves are final decisions. The point is we could take a new sample like this one, which has no for sunny and yes for 90 degrees, and run it through the tree and make a prediction. So on day 5, should I go outside? Well, it's not sunny and it is greater than 90 degrees. So if it is greater than 90 degrees, we go to the right and we say no. It's too hot, don't go outside. We got the same result when we used the other tree, when we started with sunny. There are many different ways to build a tree, and we'll learn a specific way using entropy and information gain a little bit later in this lecture. One thing to note is that in this particular training set, we have every possible combination of features. We have yes, 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 no, no, yes, and no, no. So there's nothing we've not seen before, right? And there's no samples that contradict each other. We could have a sample, let's say, no, no, and the outside label is yes. In that situation, we could never get 100% accuracy on the training data. We use a greedy algorithm to build the decision tree. That's what we were doing before. And we decided to split using accuracy, right? But it kind of was random. And our first split gave us a 75% accuracy. And we could have just said no all the time and gotten 75% accuracy. So there's got to be a better way to split. What we're going to use is called entropy and information gain. we're going to use the definition of entropy that's a part of information retrieval. Entropy is a very complicated concept, and almost every field has a different definition of it. In this class, you can think about it as surprise. The more information that's contained in a set of data, the more surprise you have, right? The example I used in class was, if I come home every day and my dog is very excited to see me, and I come home one day and the dog is still very excited to see me, nothing is new. Nothing unexpected happened. If I come home the next day and my dog is not excited, doesn't come to the door, seems kind of lethargic, that's a cause for concern. Suddenly there is new information. Okay, so something surprising gives us new information. You can think about entropy in the same way. Entropy uses a capital H. In this class, we're going to use kind of a weird notation so we can use all of the different splits properly, and we can use a notation for that gets long but is very informative. So here we have H with empty parentheses. So this is the entropy of the whole set. So there's no conditions inside of the parentheses. Okay? The entropy of a set is simply the sum of the probability of each class multiplied by the log of the probability of the class. Little c is going to be the class, and big C is the set of classes. What are the classes? No and yes, right? That's the labels, no and yes. And so all this is the sum of the negative probability of no times the log of the probability of no plus the negative probability of yes times the log of the probability of yes. It's a lot. We're going to really take it slow and go through each part of this. First, it's probably been a long time since you've had to deal with logs, okay? I know I have to refresh them a lot, so don't worry about that. Remember that a log of a number is simply the base to some y equals that log, okay? So what we have here is the base is 2. So log 2 of x is 2 to the y equals x. So we're trying to find y, okay? So log 2 of x is this y that the 2 is raised to. 2 to the what equals the number inside of the log. I know it's a lot. Let's look at an example. Log base 2 of 4. Okay, so we have 2 to the y equals 4. So what number does y need to be to get 4? Y needs to be 2. So the log base 2 of 4 gives us 2. Another example. 2 to the what equals 1/2. Turns out log base 2 of 1/2 is -1. Don't worry too much about it. I just want to make sure you have an understanding of what it is so you don't panic. Quizzes and exams will include a table or samples of log values so that you don't have to worry about it. Calculators are not allowed on quizzes and exams, so this is the way that I get around that. Let's look at some examples so we have a better sense of what's actually going on here. Here I visualized the log function so you can see what it looks like. And here we have a set of sample data. So you can see here we don't have any features because in entropy we're not really worried about the features, we're worried about the label, okay? So let's pretend like there's a couple features there that we just can't see. And we have 4 samples and 4 outputs. So we have 4 labels. And all of them have a label of no. Okay, so let's calculate entropy and see what's going on here. Entropy here is going to be the negative probability of no. What's the probability of no? Well, in this particular data set, it's 100%, right? We have a probability of 1 that will say no. We always say no. So it's going to be -1 log 2 of 1, right? Plus the probability of yes, plus the negative probability of yes, right? And what's the probability of yes? Well, we never say yes. We always say no. So the probability of yes is going to be 0. So it's going to be 0 log 0. Okay? What does that reduce to? It reduces to -1 times 0 plus 0 times -infinity. 0 times -infinity is going to be 0. Okay? The 0 always wins. So the entropy in this case is 0. What does that mean to me? That means there's nothing interesting here, nothing surprising, there's no information. Okay? That shouldn't be surprising, right? Because all we see are no's. So it's kind of like every day coming home and your dog is excited. It's the same thing over and over again. Now, if we look at the opposite case, where it's always yeses, we get the exact same result. It's still unsurprising. Okay? Now for a more interesting case, if we have 4 samples, 2 of which have a label of yes, and 2 of which have a label of no, we get a more interesting value for entropy. What's our probability of no? Our probability of no is 1/2. Okay, what's our probability of yes? It's 2 out of 4, so again, it's going to be 1/2. So then our entropy becomes negative 1/2 log of 1/2 minus 1/2 log of 1/2. So what is that? It's 1. Okay, remember the log of 1/2 is negative 1. So we reduce all that and we get an entropy of 1. So this is the most exciting entropy we can have because everything is pretty random. Okay, so everything is surprising. If we look at another example, when we have 3 yeses and 1 no for our label, then our probability of no is going to be 1/4, and our probability of yes is going to be 3/4. This ends up making our entropy 0.811. Okay, so it's going to be less exciting than the previous example, but more exciting than if everything is the same. Okay, now that we know what entropy is, we can talk about information gain, which is what we're going to use to make splits with our decision tree. Information gain is simply the entropy of the full set minus the probability that I ended up in a particular side of a split times the entropy of that split. It sounds complicated, but trust me, it's not. I think it's best to go through an example first. Let's look at our tree that we built when we were dealing with this set of data, trying to decide if we wanted to go outside. With our question Sunny, we have samples 3 and 4 on the left-hand side and samples 1 and 2 on the right-hand side. And remember, we said no on the left and yes on the right. Let's think about what's happening here in terms of entropy and information gain. First, we need to calculate the entropy of the whole set. Okay? So we do that by calculating the probability of no, which is going to be 3/4, and then the probability of yes, which is going to be 1/4. And then we calculate the entropy, and we get 0.811. Okay, so that's the entropy of the whole set. Now we split on Sunny, so now we have 2 subsets. We have the subset with 3, 4 and the subset with 1, 2. We want to see if we gained any information by splitting in this way. So we need to calculate the entropy of the left side and the entropy of the right side. So the entropy when Sunny equals no is going to be this equation on the left. This is the reason we use these parentheses, so we can start adding conditions inside of them. And these conditions create these subsets. Okay, so the condition Sunny equals no creates the subset of samples 3 and 4. Okay, and the entropy of that subset is 0 because both samples have a label of no. Make sure to calculate that out on your own and make sure you get 0. Now on the right-hand side, we have the subset where Sunny equals yes, which includes samples 1 and 2. The entropy on this side is 1 because it's 50-50. Make sure you calculate that on your own and you also get 1. Now that I have the entropy of both of my sides after my split on Sunny, I can calculate information gain. Information gain, remember, is the entropy of the whole set minus the probability that I ended up on one side of the split times the entropy of that side of the split plus the probability I ended up on the other side of the split times the entropy of that side of the split. So on the left side, what's the probability that I ended up on the left side of this split? Well, there's 2 samples on the left side of the split and there's 4 samples that we started with. 2 out of 4 is 1/2. Similarly, on the right-hand side, we ended up with 2 samples out of 4 total. So it was 1/2 probability that I ended up on the right-hand side of the split, I being a sample. We calculate this out, and we get 0.311 as the information gain. What do we want? We want both sides of the split to have an entropy of 0. If both sides of the split have an entropy of 0, then our information gain will be very high. Remember that when we were using accuracy, we split here, and it was no better than making no tree at all. So information gain works a little bit differently, and it'll actually help us build a better tree. Because our information gain was not the same as the entropy when we started, that means we still have things to learn, and so we want to keep going. This brings us to the greedy algorithm that we're going to use to build the tree. Okay? It has roughly 4 steps, although you don't need to remember them or write them down in this particular order, whatever works for you. First, we want to calculate the entropy of the entire training set. Second, we want to split the training data using each feature and calculate information gain for each split. Third, we want to choose to split on the feature that gives the best information gain, best being maximum. And 4, we want to repeat these steps, 2 through 4, on each subset until the best information gain is 0, meaning we can't really do anything else, or we run out of features. This is a recursive process. It's probably been a little while since you've used binary trees or implemented them or done anything with them, but you may remember that binary trees are built with a recursive process. Now, as far as your projects are concerned, I don't really care if you implement it as a recursive process or an iterative process, because as you know, just because it's recursive doesn't mean you have to implement it that way. Let's run through an example. Now that you understand how it works, let's make sure that you can actually do it. We're going to use this data set for the rest of the presentation. This consists of 10 samples of different TV shows. And there's features including, is the show less than 40 minutes? Is the show a comedy? Does the show have a female lead? Is the show political? And the label is going to be, do I like the show? Okay? So this is a very small portion of basically a data set that Netflix would use to predict new shows for you to watch. Okay? Let's build a decision tree such that I can predict whether or not I will like new shows. Let's start with our greedy algorithm. First, we need to calculate the entropy for the entire training set. I highlight all of the yes labels in green throughout, okay, so that we have a better way to visualize how many samples are yes and how many samples are no. So here we have 4 samples of yes and 6 samples of no. So we calculate entropy like so at the bottom of the screen, and we get 0.97. So not quite random, but pretty close. Now we want to split the training data using each feature and calculate the information gain for each split. If we split on less than 40, which is going to be all of these blue samples, okay, we see that if we look at only the samples where less than 40 is no, there's only one of those that is labeled as yes, okay? So we'll get 4 out of 5 correct if we just say no. Okay, so the probability of no is 4 out of 5, and the probability of yes is 1 out of 5. Okay, that means our entropy on this side is going to be 0.72. Now let's look at the right side. If the show is less than 40 minutes, then we have 3 out of 5 yeses and 2 out of 5 no's, and our entropy ends up being 0.97. What's the information gain if we split this way? Remember that the entropy on the left side is 0.72 and the entropy on the right side is 0.97. The entropy for the entire set is 0.97. And so we're going to subtract the proportion of samples on the left side with the entropy of the left side and the proportion of the samples on the right side with the entropy on the right side. Okay? Remember, there's 5 samples on the left side and 5 samples on the right side, and there were a total of 10 samples. Our information gain with this split is 0.12. Now we'll move on to the next feature, comedy. The samples shown in blue have a feature of comedy equal to yes. If we look at the no samples, the samples with a comedy feature of no, we see there's only 1 out of 6 that's labeled with yes, and the rest are labeled with no. We calculate entropy on this set, and we see that it's 0.65. As you can see, I had a note here to stop for a top hat question. Moving on the right-hand side, when comedy equals yes, we have 4 samples, 3 of which have a label of yes. The entropy for this side is 0.81. With the entropy on the left side calculated and the entropy on the right side calculated, we know there's 6 samples on the left and 4 samples on the right, and so we calculate information gain like so, and we get 0.25. Moving on to the next feature, which is female lead. All of the samples in blue have a female lead value of yes. If we look at no first, we see that all of them have a label of no, and this gives us an entropy of 0 on this set. On the right-hand side, when female lead equals yes, we see that 4 out of 7 samples have a label of yes, and 3 out of 7 samples have a label of no. This gives us an entropy of 0.98. Calculating information gain, we know there's 3 samples on the left side and 7 samples on the right side, and it gives us an information gain value of 0.28, which is the highest one we've seen so far. Our final feature, political, has 5 samples with a value of yes and 5 samples with a value of no. If we look at the no samples first, we see that there's 3 no's and 2 yeses. Okay? This gives us an entropy value of 0.97. If we look at the yes samples, we see that there's 2 yeses, 2 that we like, and 3 that we don't like. This gives us an entropy value of 0.97, and we end up saying no on both sides. This doesn't look good. We know that there's 5 out of 10 samples on the left and 5 out of 10 samples on the right, and so when we calculate information gain, we see that it's 0. It would make absolutely no sense to split on the feature political right now, because we would do just as well as if we just said no. Okay, that's what this is telling us. Let's look at our options. We finished splitting the data on each feature, and now we need to choose the best feature to split on, okay? Looking at all the features and their associated information gains, which one looks the best? Female lead. It has the highest information gain, so we'll start with that. If we stopped right now, how would our model do? Okay, our model would actually get 70% accuracy based on female lead. So if we were using accuracy to build our tree, we would start with comedy, not female lead. Now, step 4 of the algorithm is to repeat steps 2 through 4 on each subset until the best information gain is 0. Okay, that means there's nothing left to learn, or we run out of features to split on. We're looking at the left side of female lead, which is when female lead equals no. In that case, we don't seem to like any of those TV shows. The information gain there is 0, which means there's nothing left to learn. the entropy here is no, which means we're done, right? We can just predict no, and we'll get 100% accuracy on that side of the tree. Now let's look at the right-hand side, when female lead is yes. In this case, we have 4 out of 7 yeses, yes, I like it, and 3 out of 7 no's, I don't like it. This gives us an entropy of 0.98. Why are we calculating this again? Because when we start working with information gain as we continue to split, we don't really care about the entropy of the whole set anymore, right? Because there's those 3 samples on the left that we have nothing to do with anymore. So our new entropy that we're going to be using at the beginning of the information gain equation is going to be this one, the one where we're dealing only with the subset of female lead equals yes. Okay, let's start with our first feature, negative, less than 40 minutes. The samples that are blue have a yes value for the feature of less than 40 minutes. On the no side, we have 1 sample that we like and 2 samples that we don't like. So the entropy here is going to be 0.91. The notation is starting to change a little bit, as you can see on the left side of the equation. Here we have the entropy of female lead equals yes, and, which is denoted by this comma here, less than 40 minutes equals no. Okay? Because we're dealing with the subset of female lead equals yes from the start. And then we're adding features, including, right now, the 40 minutes. The entropy for this subset, which is going to be the left-hand side, is 0.91. Now on the right-hand side, when less than 40 minutes equals yes, the entropy is going to be 0.81 because we have 3 likes and 1 no. The information gain for this particular split is going to be the entropy of female lead equals yes minus all of this stuff. So it looks like a lot, but let's think about it. For female lead equals yes, there's 7 samples total. On the left-hand side of the 40 minutes split, we have 3 samples. And on the right-hand side, we have 4 samples out of 7. So we calculate entropy like this. And the information gain is going to be 0.12. Make sure you calculate this on your own and you're getting the same numbers. It's very important that you understand this process. Now let's split on something else. Let's try comedy. For comedy, we only have 3 samples that have a comedy value of yes, and 4 samples with a comedy value of no. For a comedy value of no, there's 1 that we like and 3 that we don't. This gives us an entropy of 0.81 on that side. On the other side, when comedy equals yes, we like all of those shows. So we have an entropy of 0. That's great news. The information gain is then calculated as follows, and we get 0.52, which is very large. This is looking good. We still have to check the final feature. Why do we not check female lead again? It doesn't make sense to do that. We can ask again about female lead, but we'll just continue down the right side because female lead already equals yes. Doesn't make sense to ask another question about it. So we ask about political instead. There's 4 samples with a yes value for political and 3 samples with a no value for political. On the no side, 2 we like and 1 we don't. This gives us an entropy of 0.91. On the right-hand side, there's 2 that we like and 2 that we don't. This gives us an entropy value of 1. Calculating information gain, we get a very low value, 0.03. That's because the entropy was 1 on the right side and 0.91 on the left side. Pretty high values. These are our 3 options, okay? Don't forget we need to pick one now, okay? We pick the one with the highest information gain, which is going to be the one in the middle with comedy. Now that we've looked at this and decided that comedy is the best one to go with, we want to see where we're at, okay? So if comedy equals yes, it turns out We get all of them right if we say yes. And our entropy is 0. So we're done on the right-hand side of this tree. Okay? Now we're going to look at female lead equals yes and comedy equals no. In this case, we have an entropy of 0.81. Still pretty high, so we can keep improving. What we're going to do is we're going to ask about the two remaining features, less than 40 minutes and political. And we're going to see if we can do better. For less than 40 minutes, we only have 1 out of 4 samples with a yes value. On the no side, we get 2 out of 3 right if we say no, and 1 out of 3 right if we say yes. The entropy on this side is 0.91. For 40 minutes, yes, we see that all of them are no because there's only 1 sample. Okay, so the entropy in this case is 0. But this looks bad, right? If we're saying no on both sides, there's no real reason we needed to ask a question. Let's look at the next. Oh, before we look at the next feature, let's calculate the information gain. The information gain looks a little bit more complicated, but that's just because we're using this notation. So now we're only dealing with the entropy at female lead equals yes and comedy equals no, right? So we're only dealing with those 4 samples. And we end up with this information gain of 0.12, so pretty low. Make sure you calculate this on your own and get the same value. Let's try political instead of less than 40 minutes. Political has 2 samples with a yes value and 2 samples with a no value. On the no side, we see that it's random, right? We see that there's 1 that we like and 1 we don't like, okay? So that means the entropy is pretty high, it's 1. On the other side, if political is yes, it seems like we don't like any of those shows, right? So the entropy is going to be 0. Let's calculate information gain. For this tree with female lead, comedy, and political, we only have 4 samples that are yes for female lead and no for comedy. And so they go into this question of political. Turns out there's 2 samples with a no value for political and 2 samples with a yes value for political. And so information gain is calculated as follows. There's a little less than sign in the political thing that should not be there. Doesn't really matter. There's a little less than sign. Ignore it. We can see that the information gain is 0.311. We've built 2 trees now. The left-hand side, with female lead, comedy, and less than 40 minutes, has an information gain of 0.12, and the right-hand side, with female lead, comedy, and political, has an information gain of 0.31. So we're going to choose the tree on the right-hand side because we want to maximize the information gain. Now let's see where we're at. So if we ask female lead yes, comedy no, and political yes, we see that we have 2 samples and they both have a value of no for like. That means that our entropy is 0 on that side and we're done and we can just say no. Moving on to the left-hand side, we see that if it's yes, it's a female lead, no, it's not a comedy, and no, it's not political, we're pretty split on it. We like one of them and we don't like the other. And so our entropy is 1, which means we should be able to improve. We ask the only question we can ask, which is the 40 minutes feature. Turns out there's 1 sample on the left-hand side and 1 sample on the right-hand side. And for 40 minutes is no, we get an entropy of 0, and we say yes. And for 40 minutes is yes, we get a value of no and an entropy of 0. What's our information gain? Our information gain is 1. We started with a value of 1 because we had 2 samples. We had an entropy value of 1 because we had 2 samples, one with a like value of yes, one with a like value of no, completely random. And so that's an entropy of 1. And then we subtract 1/2 times an entropy of 0 and 1/2 times an entropy of 0, and we get an information gain of 1. So now that our information gain has been maximized, we're done. There's also nothing left to split on. This is our final tree. We can ask about female lead, and then we can ask about comedy, and then we can ask about political, and then about 40 minutes. Why do we build this tree? So that Netflix can recommend new shows. So if we have Brooklyn Nine-Nine, we know that Brooklyn Nine-Nine is less than 40 minutes. We know it's a comedy. We know that the lead is actually a male actor, and we know that it's not political. Okay? So we can say, okay, am I going to like it or am I not going to like it? Well, what we do is we see, okay, it's not a female lead, and so we immediately go to the left and we say, no, I'm not going to like it. Okay? This may not be true because this model has only seen 10 samples, right? It doesn't necessarily know exactly what you like. It only knows from those 10 samples. And so it's not going to recommend Brooklyn Nine-Nine to you because there's no female lead. What about this next one? So this one has a female lead, younger. So we go to the right-hand side and now we ask about comedy. It's also a comedy, and so we go to the right-hand side and we say yes. Okay, so we're going to like younger because it's a comedy with a female lead. This is our greedy algorithm again. It has roughly four steps, and it works pretty well. Decision trees are used a lot in a lot of different areas. NASA uses them to identify different areas of terrain to decide what is traversable and what is not for different rovers. So that's pretty cool. It's always a good baseline to test out if you're doing a machine learning problem because they work pretty well and they're pretty easy to train. And yeah, so today we learned about decision trees, and they're a model and an algorithm, right? So I told you we were going to learn what is a decision tree and how do we generate one. So a decision tree is a model, and it happens to be a binary tree. And how do we generate one? With a greedy algorithm. And in this class, we use information gain as a part of that greedy algorithm.